Hey everyone, welcome to Bayao Tutorials. In this video, we will solve again a fluid mechanics problem from the book of Yunus A. Sengel and John M. Simbala, Chapter 7, Dimensional Analysis and Similarity, Problem 7-38. So, repeat problem 7-37 as you can see or visit our recent video, with all the same conditions except that the only facility available to the student is a much smaller wind tunnel. Their model submarine is a 1/24th scale model instead of a 1/5 scale model. At what airspeed do they need to run the wind tunnel in order to achieve similarity? Do you notice anything disturbing or suspicious about your result? Discuss your result. So, in this problem, which is related to problem 7-37, for a scale model of submarine being tested in air, we are to calculate the wind tunnel speed required to achieve similarity with the prototype submarine that moves through water at a given speed. So our assumption in this problem is the compressibility of the air is assumed to be negligible. The wind tunnel walls are far enough away so as to not interfere with the aerodynamic drag on the model sub. And the model is geometrically similar to prototype. So we have here the properties given. For water at temperature 15 degrees Celsius and atmospheric pressure, our density is 999.1 kilogram per cubic meter, and our mu is equal to 1.138 times 10 raised to negative 3 kilogram per meter times second. For air at temperature 25 degrees Celsius and atmospheric pressure, our density is 1.184 kilogram per cubic meter, and our mu is equal to 1.849 times 10 raised to negative 5 kilogram per meter times second. So our analysis is that the similarity is achieved when the Reynolds number of the model is equal to the prototype. So here our Reynolds number is equal to the density m times velocity m times length m all over by mu m, which is equal to the Reynolds numbers of P is equal to the density of P times the velocity of P times the length of P all over by mu P. So we solve, this is our equation 1. We solve equation 1 for the unknown wind tunnel speed. So we have formula Vm is equal to Vp times mu m over mu p multiplied by density p over density m multiplied by the length p over the length m. So substituting all the values we had 0.440 meter per second multiplied by 1.849 times 10 raised to negative 5 kilogram per meter times second divided by 1.138 times 10 raised to negative 3 kilogram per meter times second multiplied by 999.1 kilogram per cubic meter divided by 1.184 kilogram per cubic meter multiplied by 24. So solving this or calculating this in our calculator, we get 145 meter per second. So this is our velocity in m. So this is our final answer, and At this air temperature, the speed of sound is around 346 meters per second. Thus, the Mach number in the wind tunnel is equal to 145 divided by 346, that is equal to 0.419. The Mach number is sufficiently high that the incompressible flow approximation is not reasonable. So the wind tunnel should be run at a flow speed at which the Mach number is less than 1/3 of the speed of sound. At this lower speed, the Reynolds number of the model will be too small, but the result may still be usable, either by extrapolation to higher Reynolds number, or if we are fortunate enough to have Reynolds number independence as discussed in previous topics. So again, this is the answer in our problem. So that's it for today's video. Thanks for watching and see you again on our next one. Happy learning!